So welcome to this Reigate further maths video, year 2 core pure complex numbers, and we're going to use de Moivre's theorem this time to derive trig identities for powers of cosine or sine of theta. I'm going to share the visualizer with you. There we go. So first of all, we need to find some identities that we are going to be using. So what we're going to do again is we're going to write Z. We're going to say Z is a complex number. We're going to write it in its modulus argument form, cos theta plus I sine theta. So we're now going to look at 1 over Z, which is equal to Z to the power of -1. So that's cos theta plus I sine theta, the power of -1. And de Moivre's theorem tells us that is equal to cos of minus theta plus I sine of minus theta, which is equal to, well, cos of minus theta is just equal to cos of theta, so this is cos of theta. And sine of minus theta is equal to minus sine of theta. So this is cos theta minus I sine theta. It is important to remember this. You don't need to derive this. You can just write down 1 over Z is equal to cos theta minus I sine theta, but it doesn't do any harm to see it again. We've also got Z to the power of n is equal to cos n theta plus I sine n theta. Let's put brackets around the n theta. That's what de Moivre's theorem tells us, that this to the power of n is this. And Z to the minus n is equal to cos n theta minus I sine n theta. We get to this by a similar method to this. So why are we writing all this down? Well, because Z plus 1 over Z is equal to, so we're going to add this together, add this to this. When we do that, the positive I sine theta here and the negative I sine theta here cancel each other out, and we get 2 cos theta. We also get Z minus 1 over Z. Well, if we do that, now cos theta minus cos theta, those cancel each other out. We've got I sine theta minus I sine theta, so that's equal to 2I sine theta. So those two things are very useful. We'll see why in a moment. We've also got Z to the n plus Z to the minus n, or 1 over Z to the n is equal to 2 cos of n theta, and Z to the n minus 1 over Z to the n is equal to 2I sine of n theta. One thing that I find I'm a bit prone to is forgetting to write the I in here or here. So watch out for that. Obviously, it's very important to get that correct. So why do we care about that? Well, let's have a look at the question in the course workbook. Express cos to the power of 4 of theta in this form in terms of cos 4 theta and cos of 2 theta. So what we're going to do here is we're going to say let Z equal cos theta plus I sine theta, and then we're going to say that z plus 1 over z is equal to 2 cos theta, which we've just seen. If you're doing this in the exam, you can just write this down. You don't need to justify it unless you're explicitly told to. So we can now write z plus 1 over z to the power of 4 is equal to 2 cos theta to the power of 4, which is 16 cos the power of 4 of theta. We want an identity for cos the power of 4 of theta. So 16, we're going to turn this the other way around, cos the power of 4 of theta is equal to. The other thing that we can do is we can use a binomial expansion on this. So this is z to the power of 4 plus 4z cubed times 1 over z plus 6z squared times 1 over z squared plus 4 z times 1 over z cubed plus then we've got 1 over z to the power of 4, z power of 4. Now, if we put together these terms, well, first of all, if you look at the middle one, actually no, let's look at the outside terms first. So this is z to the power of 4 plus 1 over z to the power of 4. Let's write that out. So z to the power of 4 plus 1 over z to the power of 4. And then we've got 4 times, well, z cubed over z is z squared, so this is z squared. Here we've got z over z cubed, so that's 1 over z squared, 1 over z squared, plus, and here we've got z squared over z squared, so this is just 6. Now, we know that z to the power of 4 plus 1 over z to the power of 4, in a similar way to this, is 2 cos of 4 theta. So that's 2 cos 4 theta plus, this is 4 cos of 2 theta plus 6. So now all we need to do is divide through by this 16, so we can say cos the power of 4 of theta is equal to, well, 2 over 16 is 1 over 8. So 1 over 8 cos of 4 theta plus 4 over 16 is a quarter. So a quarter cos 2 theta plus 6 over 16, which is 3 over 8. And we've shown this trig identity. So our A is equal to 1 over 8, B is equal to a quarter, and C is equal to 3 over 8. Okay. A equals 1 over 8, B equals a quarter, and C equals 3 over 8. We can do a similar thing with sine. So again, we're going to say let z equal cos theta plus I sine theta. Let z equal cos theta plus I sine theta. Please try and do this at the start of every question. It makes it very clear to anyone marking your work that you know what z means, and and it also helps you to keep in mind what you're working with. So z minus 1 over z is 2I sine theta. Now we want sine to the power of 5 of theta here. So what we're going to do is we're going to say, we're going to raise this to the power of 5. So we're going to say 2I sine theta to the power of 5 is equal to, well, let's write this out, z minus 1 of z to the power of 5. We're going to use our binomial expansion again, and we're going to expand what we have here. So 2I to the power of 5, well, 2 to the power of 5 is 32. I to the power of 5, I to the power of 4 is 1, so I to the power of 5 is just 5. It is just I. So this is 32 I sine the 5 of theta is, well, we've now got z to the power of 5 plus 4 z to the 5 times minus 1 over z. Don't forget the minus signs here. Plus 10 z to the power of 4 times minus 1 over z squared. Plus 10 z to the power of 4. Oh, sorry, that should have been power of 4 there and power of 3 there. Oops. There we go. So this is power of 2. I thought there was something going wrong. Z squared times minus 1 over z cubed. These sums of these powers should always add to 5. Add to this power here. So plus 5 z times minus 1 over z to the power of 4. And then we've got plus minus 1 over z, minus 1 over z to the power of 5. And that is equal to, well, we've now got, let's put these things together. This is z to the power of 5 minus 1 over z to the power of 5. Let's put these ones together. 1, 5. Why have I got 4 there? That should have been 5. Sorry, riddled with errors now. So plus 5 this is, or sorry, that should be minus 5. We could have taken away that plus, couldn't we? Minus 5. Z to the power of 4 divided by z is z cubed. So that's minus 5 z cubed. What have we got here? This is minus 1 over z cubed, or minus 5 times 1 over z cubed. So plus I think I've lost a minus sign here. Oh no, this is positive, isn't it? Minus, minus, yeah. So minus there. So for 1 over z cubed. And then this one, this is going to be positive, this is going to be negative. So it's plus 10 z cubed over z squared is z. So z minus 1 over z. So we now have, well, we know that z to the power of 5 is 2I sine of 5 theta. This is then minus 5 times 2I sine of 3 theta, so it's minus 10 I sine 3 theta, and this is plus 10 times 2I sine theta, so 20 I sine theta. And that's all equal to 32 I sine power of 5 of theta. So we've now got, if we divide through by I and also divide through by 32, another way of looking at that is divide through by 32I, we get sine the power of 5 of theta is equal to 1 over 16 sine of 5 theta minus 10 over 32, which is 5 over 16, isn't it? So minus 5 over 16 sine of 3 theta plus 5 over 8 sine of theta. So we've got an identity for sine to the power of 5 of theta, which was similar to how we found an identity for cos to the power of 4 of theta in the previous question. So that's part A of this question. Part B, well, one of the reasons for finding identities like this is that it enables us to integrate sine to the power of 5 of theta. So we can say the integral of from 0 to pi over 2 sine the power of 5 of theta d theta is, well, we're going to integrate all of this and then we're going to substitute the values in. So I'm going to say that that is, well, we're going to get, let's take out a factor of 1 over 16. So the integral of, actually it's easier to take out a factor of 1 over 32. So we're going to say that's 1 over 32, 0 to pi over 2, 2 sine 5 theta minus 10 sine 3 theta plus 20 sine theta d theta, and that is equal to, I'm going to try and squash this up to get this in here, 1 over 32 times, integrate sine of 5 theta, we're going to get minus cos of 5 theta, and then divide by 5, so minus 2 over 5 cos 5 theta plus 10 over 3 cos of 3 theta minus 20 cos of theta. From 0 to pi over 2. Up just a little bit. We're now going to substitute these values in. So this is 1 over 32 times, well, put pi over 2 in here. We've got cos 5 pi over 2. So minus 2 over 5 cos of 5 pi over 2 plus 10 over 3 cos of 3 pi over 2 minus 20 cos of pi over 2 minus, well, we're going to put 0 in each of these, so that's going to be cos of 0 is 1, so it's minus 2 over 5 plus 10 over 3 minus 20. Each of these is 0, so cos of 5 pi over 2, cos of 3 pi over 2, cos of pi over 2 is 0. We could have put those in straight away, so we've just got this. So we've now got 1 over 32 times, let's minus that, so 2 over 5 minus 10 over 3 plus 20, and that works out to a value of 8 over 15. So quite long examples there. It's quite involved working. I hope that is helpful, and we'll come back and look at another application of de Moivre's theorem for sums of series next. But I'm going to leave that there for now. Thank you for listening.